Assalamu alaikum. Welcome to lecture number 4 of CS 218 Data Structures and Algorithms. In the last lecture, we analyzed some more algorithms. We realized that there is no need to find absolute running time of an algorithm. We realized that we analyze algorithms typically for large input sizes. We were introduced to asymptotic analysis, and we conducted asymptotic analysis of algorithms. We are still continuing with analysis of algorithms. Chapter 4 of book 1 and chapter 2 of book 2 are being used for this topic. Let us spend some time with this graph showing how different functions grow. On the x-axis is input size. On the y-axis is the running time of algorithms. We can see that as the input increases, the running time of the function increases, which means that the algorithm takes more time, which means that the algorithm slows down. Consider the two linear functions 10n and 20n. 20n is a steeper function than 10n. There is a function here 5n log n, which is called the linear-rhythmic function. This function grows faster than both the linear functions, but slower than the quadratic function 2n squared. As the degree of the polynomial increases, the steepness of the curve increases. For n greater than 5, the algorithm with running time 2n squared is already much slower. This happens even though 10n has a greater constant factor than 2n squared. We can assume that any cubic function would grow even faster than 2n squared. Now we come to the exponential or the geometric function 2 raised to n. You can see that the curve shoots upward as n increases. But the fastest of all is the factorial function. Though the logarithmic function log n is not shown here, we can predict that it grows slower than both linear functions 10n and 20n. Have a look at another graph. Here you see a blue line that is flat. This is a constant. No matter how much you change the input size, the graph of the constant function, which in our case is 600, is never affected. We say that the constant function does not grow at all. After the constant function, the least growth is exhibited by the logarithmic function 40 log n. A faster growing function than this is the linear function 17n. But even though 17n is faster, it is still no match for the linear-rhythmic function 5n log n. The one with the steepest curve is the quadratic or n square function. It would be a good idea to arrange all our functions with respect to their rates of growth. And this is exactly what we are going to do. So the function that never grows is the constant function, as we saw. Faster than this is the log n function. Faster than this function is the logarithmic function. And if you take a power to the logarithmic function, you will get the polylogarithmic function log of n whole raised to the power a. Now people may ask, what is the difference between log n and log of n whole to the power a? First of all, in computer science, we work with binary formats, so all logs are to the base 2. Now, to compute log n, we first compute the log of n, then the log of this answer. So the answer gets even smaller. To compute log n raised to a, we compute log of n, then we multiply the answer with itself a times. So the number grows. Faster than the polylogarithmic function is the linear function. And a function that is faster than the linear function is the linearithmic function. This function we also saw in our previous slides. Obviously, after this, I will have the quadratic function. I have lumped the quadratic, cubic functions into one function which I call here the polynomial function. This is n raised to a, where a is an integer and greater than 1. Faster than the polynomial function is the geometric or exponential function a raised to n. Then we have the factorial function. And even faster than the factorial function is n raised to the power n. If you ask how I came to this conclusion, let me show you. N raised to the power n can be written as n n's. N factorial is written as n terms again, but these terms are decreasing. If you look at the two equations that I have placed in front of you, you will be able to see that n raised to the power n will always be a larger value than n factorial. Some people may argue that analyzing algorithms takes effort, and a relatively easier solution is to upgrade the machine that you have. This will automatically speed up execution of the algorithm. We want to understand if this is a good approach. Suppose we have the budget to get a faster machine. Let us see if a faster computer will speed up our algorithms. Moving to a faster machine. Our current machine executes n data items per hour. Suppose we purchase a new computer that is 10 times faster than the one we have. Assume that the new machine executes m data items per hour. We are hoping that the new machine, being faster, will be able to execute our algorithm on more than n data items in an hour, that is, m will be greater than n. Writing the formula for speedup. Speedup is time expended on the larger dataset divided by time expended on the smaller dataset. In our case, this can be written as time of m data size divided by time of n data size is 10. Now that I have a machine which is 10 times faster than the previous one, let us look at how algorithms of logarithmic growth rate react to it. Suppose I have an algorithm whose running time is 2 log n. I put this value in the equation that I just showed you and I get this equation. 2 log m divided by 2 log n is 10. Cancelling the 2's in the numerator and the denominator, I get this equation. log of m is 10 log n. 10 can be taken to the power of n according to the rules of log, and we would have this: log of m is log of n raised to the power 10. Remember that this log is to the base 2, so I raise both sides of the equation by 2. This cancels the log, and I am left with m is equal to n raised to the power 10. This was one algorithm which was logarithmic, and now I have another. The running time of the second algorithm is 5 log n. Again, I put this value in my equation of speedup, and I get to the same sequence of equations that I have just gone through. Look at this table. If the running time is 2 log n, the new data size, or the larger data size that my new machine can churn in the same 1 hour, is n raised to 10. So if my previous machine was processing 1000 data items in an hour, my new machine is processing 1000 raised to the power 10 data items, which is quite a speed up. Actually, it is a speed up larger than the speed up of the machine. The speed up of the machine was only 10, but the improvement in data size is a lot more than 10, as you can see here. The curious thing is, for both logarithmic algorithms, the improvement in data size is the same. Let us investigate this further. Now I work with algorithms of linear growth rate. Suppose my algorithm has a running time of 10n. The speedup equation remains the same, and I put this value in it, and I come to this equation. M is 10n. Let us take another algorithm which is linear. This time the running time is 50n. Putting this value in the speedup equation, I still get to the same improvement in problem size. So, if the running time of an algorithm is 10n, then the new machine can churn 10 times more data than the previous machine. So if the previous machine was handling 1000 data items in an hour, the new machine can handle 10,000 data items in the same hour. So I am getting as good a speed up for the problem size as the speed up of the computer. Also notice that the improvement in problem size for the linear algorithm is lesser than the improvement in problem size for the logarithmic algorithm. Again, we see that no matter what constant I use with my function in the running time, the effect on the problem size is the same. Now we work with algorithms of quadratic growth rate. My first algorithm has a running time of 20n square. Putting this in the speedup equation, I come to m square is 10n square, which can be simplified to m is under root 10 into n. The under root is on 10 only. If I have a quadratic algorithm whose running time is 75n square, I get the same improvement in data size. So if you have a quadratic algorithm, and if your previous machine was able to process 1000 data items in an hour, the new machine, which is 10 times faster, will be able to process around 3000 data items in the same hour. Now we notice that the improvement in problem size is getting smaller and smaller as the rates of growth of algorithms are going up. The linear algorithms had better improvement than the quadratic algorithm. And again, the constant is not affecting the improvement in problem size. Algorithms of cubic growth rate. My first algorithm has a running time of 3n square. Putting this value in the speedup equation, I come to this equation. M cube is 10 into n cube, which can be simplified to m is the cubic root of 10 times n. Again, the cubic root is on 10 only. My second algorithm has a running time of 8n cube, and again we come to the same conclusion. So for cubic growth rate algorithms, if the previous machine was processing 1,000 data items in an hour, a 10 times faster machine is only processing 2,000 data items in the same hour, which is not impressive. What about algorithms of geometric growth rate? Tn is 2 raised to the power n. Putting this in the speedup equation, I come to this equation. 2 raised to m is 10 times 2 raised to n. I apply log to the base 2 on both sides of the equation. On the left, log to the base 2 and 2 get cancelled. On the right, I use the rule log of a into b is log of a plus log of b. I get this equation. M is log of 10 to the base 2 plus log of 2 raised to n to the base 2. In the last term, again log and 2 cancel each other out, and I get this equation. M is n plus log of 10 to the base 2. Log of 10 to the base 2 is 3 point something. Let us look at another geometric algorithm with a running time of 5n. Putting this in the speedup equation, I come to this equation. 5 raised to m is 10 into 5 raised to n. This time, I apply log to the base 5 on both sides. And going through the same procedure, I get to this equation. M is n plus log of 10 to the base 5. Log of 10 to the base 5 is 1 point something. Now we look at our table and we see that with the first geometric algorithm, the new machine, which is 10 times faster, only executes 3 data items more, which is not good at all. With the second geometric algorithm, with running time of 5 raised to n, the new machine executes only 1 data item more. This is dismal performance. There are more than 1 points to note in the analysis that we have done so far. The value of the coefficient does not affect the improvement in problem size gained by a faster computer. The improvement in data size only depends on the growth rate of the function describing the running time of the algorithm. We saw this again and again. When we looked at two logarithmic functions, no matter how their coefficients changed, the improvement in problem size was the same. When we looked at two linear functions, even though the coefficients were vastly different, the improvement in problem size was the same. The same thing happened for quadratic functions. The same thing happened for cubic functions. In geometric functions, there was a slight difference of value in the improvement of problem size. But again, the improvement was negligible and the slight difference was also negligible. So we come to the conclusion that the coefficient associated with the function describing the running time is not important. And when we are analyzing algorithms asymptotically, we can forget about the coefficient of this running time function. The second point to note is the increase in problem size for an algorithm with exponential growth rate is by a constant addition, not by a multiplicative factor. Exponential growth rate is radically different than polynomial growth rates. When we were working with the algorithm with a running time of 2 raised to n, we came to the equation m is n plus log of 10 to the base 2. And when we were working with the second geometric algorithm 5 raised to n, we came up with the equation m is n plus log of 10 to the base 5. So the improvement happens by a constant addition. And this is decimal improvement, or this is improvement which we don't even consider. Think of this way. You got yourself a machine that is 10 times faster. So it might be 10 times more expensive than your previous machine. So this means that you paid 10 times the money for your previous machine. And then you ran a geometric algorithm and you got a very bad improvement in data size of just 3 more data items or just 1 more data item. This is a huge waste of the investment that you made in the new computer. A person would be completely turned off if he came to know that after spending so much money, this is the only improvement that he is getting. And then we have this result as well. The improvement in problem size for an algorithm with slower growth rate is much larger than for a faster growth rate. Look at the logarithmic algorithms. They scaled beautifully over the new machine. The linear algorithms were only as good as the machine. The machine was 10 times faster. The algorithms, the linear ones, were 10 times better. But the quadratic algorithms were only 3 times better, although the machine was 10 times faster. The cubic algorithms were only 2 times better, and the geometric algorithms were pathetic. So a bad algorithm will not let you take advantage of a fast machine, no matter how fast the computer is. From what I have seen so far, the investment in hardware is not taking me to better results. The current algorithm that I have, algorithm A, is a quadratic algorithm with a running time of n square. So when I give it 2048 data items, it takes 4194304 units of time to compute all these items. A friend proposes another algorithm B that does the same thing, but this algorithm is linear rhythmic. That is, the running time is n log n. When I give algorithm B 2048 data items, it takes 22528 units of time. This means that the execution improves by a factor of 186 without changing the hardware. So I conclude, don't change the computer. change the algorithm. Summing it all up, the notion that the effects of a bad algorithm can be mitigated by a good machine is utterly false. To reap full benefits of your investment in hardware, you must find a slick algorithm, which means that you must learn data structures and algorithms. And you're stuck with me. Consider the two functions shown here. These are 10n and 2n squared. Notice that they cross each other at n equals to 5. In this graph depicting 20n and 2n squared, we see that the two functions cross each other at n equals to 10. 10n and 20n are both linear with different coefficients. 2n squared is quadratic. The coefficient does not determine if two curves cross each other. It only determines the point at which the two curves cross each other. Are coefficients important? Suppose the old algorithm was cubic and the new algorithm is quadratic in growth rate. The coefficients in the running times of the two algorithms will not affect the improvement in problem size, will only affect the point of intersection of the two curves. After the point of intersection, moving towards positive infinity, the curve with the larger growth rate will shoot away from the other curve. This leads us to ignore the coefficients of the function in asymptotic analysis, that is, the analysis for large input sizes. So when should we not ignore coefficients? When we are comparing algorithms for small input sizes, the coefficients cannot be ignored. My first algorithm has a running time of 10n and n is 4, so it takes 40 seconds. My second algorithm has a running time of 20n and it takes 80 seconds to execute. My third algorithm has a running time of 2n squared and this algorithm takes 32 seconds to execute on 4 data pieces. You can see that the quadratic algorithm with the higher growth rate gives a better running time than both linear algorithms just because it comes with a smaller coefficient. We must remember to consider the coefficient when comparison involves small input sizes. Now I give you some homework which will help you practice your concepts and it will also help you in preparing for examination. I am not asking you to submit it, but you may talk about it with me if you have any problems. We can discuss your problems and places where you get stuck. So the first question is, for each of the following running time expressions, how will the running time scale up as the data size n is increased 8-fold? And you have all these functions for the same question. The second question is, the running time of an algorithm is given as Tn. How long will it take to execute on a 32 GHz machine for the given input size, considering that each primitive operation takes 10 clock cycles? These are the values of Tn for which you have to solve question number 2. Question number 3 says the running time of an algorithm is given as Tn. How large a problem can it solve in 10 minutes on a processor capable of executing a basic operation in 5 nanoseconds? So what did we learn today? We arranged functions in order of their growth rates. We realized that algorithms with slower growth rates are better than algorithms with faster growth rates. We learned that the coefficients can be ignored in asymptotic analysis. And we agreed that for fast execution, we need better algorithms more than we need faster machines. So what do you need to do? Read the book. Note your questions and put them up in the relevant online session, and email suggestions on content or quality of this lecture at rujan@naduit.edu.pk. Do your homework. Please don't leave it, because if you leave it, you will have a lot of problem in any test or exam that I set you. Take care. Allah Hafiz.